So now that we've talked about the properties of parallelograms and had a little bit of time to practice with them, we're going to shift our focus from calculations with parallelograms to strategies for involving parallelograms in proofs. And we're going to start by proving the three properties of parallelograms that we saw in the previous video. So as a brief reminder, a parallelogram is the name we give to any quadrilateral that has two sets of opposite parallel sides. In this case, we see two sides that are parallel using a single red parallel arrow and two sides that are parallel using double blue parallel arrows. And we also saw three properties that come along with a quadrilateral being a parallelogram. And the one that we're going to prove in this video is the fact that in a parallelogram, opposite sides are congruent. The other two properties, that opposite angles are congruent and that diagonals bisect each other, are things that you're going to prove on your own as a part of your work and practice after watching the video. But in order to prove that opposite sides of a parallelogram are congruent, we're basically starting with the given that it's a parallelogram. ABCD is a parallelogram. And we're interested in proving that AB and CD are congruent, as well as AD and BC are congruent. So what I'm going to invite you to do now is pause the video, see if you can strategize or even complete this entire proof by yourself. I added a little bit of a hint there by drawing in diagonal BD in terms of how we are actually going to go about this, using the definition of a parallelogram that involves the parallel sides. So go ahead, pause the video, see what you can come up with. If you can do the proof on your own, great. If you want to do some strategizing and come back and see the proof being done and copy as we go along from the video, that is great too. But pause the video, see what you can come up with, and come back when you are ready to see the proof. Okay, so since we are given that ABCD is a parallelogram, what we know because of that is that AB and DC are parallel and that BC and AD are parallel. That's part of the definition of a parallelogram. Now, as with previous proofs that we've done in videos, there are a few things I'm not going to write here that you should, and that's simply to save space on the screen. First is that the first step of the proof should be that ABCD is a parallelogram. And the second step of the proof should be taking the definition of a parallelogram, which is often what we do when we're trying to prove something with particular types of triangles or quadrilaterals or other types of polygons, and that's use the definition. And so the definition of a parallelogram is exactly what we drew on the diagram, which is that AB and CD are parallel and that AD and BC are parallel. I'm going to leave these off the proof, but you should have them as the first two pieces of your proof, again, so that we can save space on the screen. Well, if we think about what we know about parallel lines, we had an entire module on the interrelationship of transversals and parallel lines that they intersect with. And we know that because of transversals and parallel lines that we have a bunch of congruent angles, which is convenient because when we're trying to prove that segments are congruent using congruent triangles as a proof, we need to rely on congruent angles. And so the first set of angles that we know are congruent come from the fact that AB and CD are parallel. And that's that angle ABD is congruent to angle CDB because of the alternate interior angles theorem involving parallel lines AB and DC. Similarly, we know that angle ADB and angle CBD are congruent because they are alternate interior angles from transversal BD, but this time with parallel lines AD and BC. So let's go ahead and write that in too. Angle ADB congruent to angle CBD, again, because of alternate interior angles theorem. Well, now we have two congruent angles, which is great. All we need is a congruent side. And at this point, we're very familiar with how to create congruent sides out of triangles that interact like this using what is one of the most useful pieces of proof, and that's saying that a segment or an angle is congruent to itself. So what do we know? We know that BD is congruent to BD because of the reflexive property, which I'm just going to abbreviate as reflex. But the reflexive property, shared side, however you want to say that. Well, now we have everything we need to be able to say that these two triangles are congruent. We want to show that segments are congruent, and one of the most effective ways we can do that is using Cpctc. So we have two angles, and the side that is included between those two angles as congruent. So we can say, using ASA, the triangle ABD is congruent to triangle CDB because of ASA. And now that we have that, that is basically everything we need. We have congruent triangles. The sides that we want to prove are congruent are corresponding parts of those congruent triangles. And so the last step of the proof is to say exactly what we want to prove in the first place, and that's that AB is congruent to CD, and that AD is congruent to BC. Why? Because of Cpctc. So there's the proof that opposite sides of a parallelogram must be congruent. And we started with just any old parallelogram, and we relied on the properties of parallel lines and transversals to create enough congruent angles, as well as the shared side and the reflexive property for the congruent segment, to be able to say that these triangles are congruent. And when we're using parallelograms as a part of a proof, or proving things about parallelograms, using the properties of parallel lines and transversals becomes an incredibly effective way of showing that we have some congruent triangles. The pitfall to avoid is making sure that you are saying the correct angles are congruent based on the parallel sides. We can extend AD, AB, BC, and CD if it's easier to see which lines are parallel relating to which alternate interior angles, if that's something that's helpful. But one of the easiest traps to fall into is saying that you want to use the fact that AD and BC are congruent, but then saying that the alternate interior angles that are congruent are based on the other sides. So just be careful about which angles are related using the transversal and particular sets of parallel sides. That's going to be true as you're going through and proving that the diagonals of a parallelogram bisect each other. That is also going to be true when you're proving that opposite angles of a parallelogram are congruent. But in this proof, we actually don't need to use any congruent triangles. We are going to use the properties of parallel lines. But as it happens, parallelograms are really nicely set up because every side can be used as a transversal for the other set of congruent, now that we know, but parallel sides. So something to help you as you're strategizing for that. But that is this proof of why opposite sides of a parallelogram are congruent, as well as some suggestions for using parallelograms and the definition of parallelograms in your proofs in the future.